Okay, so I guess we can start now. Hi, hello everyone. Welcome back to the third day of New Horizons in Scientific Software workshop. I'm Yu Sung Jung from KAIST. I will be chairing the first session of today's workshop. Our first speaker is Professor Hiromi Nakai from Waseda University. He's going to talk to us about divide and conquer DFTB method. Let's welcome Professor Nakai.
Thank you, Yu-sung. So can you hear me?
Yes.
Okay. So I'm very happy to give a talk on our program, DcDFTBMD, in this nice conference. I really thank the organizer, especially Professor Choi Ho Choi, for giving me this opportunity. So Dr. Yoshifumi Nishimura, he is a main contributor to develop our program. So this is the contents of my talk today. Okay. So I have many slides, so I skip and skip. Okay. So let me start. So in my group, we have developed several types of theory and algorithms and programs. This table summarizes such activities. Normal means a nuclear orbital plus molecular orbital. It can calculate the nuclear and electronic wave function simultaneously. DC means a divide and conquer, and it is a linear scaling method. And LUT means a local unitary transformation. It is an efficient method to construct two-component relativistic Hamiltonians. So these theories are implemented in these programs. And recently, so we are working on the machine learning techniques, so machine learning electron correlation and the kinetic energy density function. So at this moment, we have no name for this one. This is written in Python language. Okay, in 1990s and early 2000s, we modified the legacy program, such as games, to demonstrate the performance of our new theories and algorithms. However, we didn't implement our in-house code into public version of legacy program. For example, normals in games. Thus, our code could not catch up with the version of legacy program. So in late 2000 and early 2010s, we attempted to implement our code into public version of legacy programs, DC and LRD, local response dispersion, and LUT in games. By effort of legacy program team, our code can follow the version up. However, our codes get varied in various functions of legacy program. And for example, for the linear scaling case, so Mark seems to love FMO in games more than DC. Yeah, but Mark seems to like LUT more than the other relativistic method. Actually, in the games documentation, our LUT IOTC option is described like this. This is the fastest and the most numerically reliable scalar relativity method. So it is preferred over blah, blah, blah. So in 2010s, despite the great effort required, we decided to develop our own programs from scratch because I came to idea the programs under development based on our new algorithm will be able to be significantly differentiated from existing legacy programs. One is the DcDFTBMD program based on the combination of DC, DFTB, and MD. And another is a Racket program based on the combination of DC, LUT, and IOTC methods. So in the future, there will be a big issue to maintain and update our programs as legacy programs have experienced. To get a lot of users, we need to make a wider advertisement to organize workshops and so on. I expect a web platform by Choi and Jerry to link our program with legacy programs. I ask the audience to add our program to your solver list. Okay, so I explained the divide and conquer method briefly as a background of our study. So divide and conquer SCF is based on the locality of the AO-based Fock matrices and the density matrices. And one of the features of DCSF scheme is to involve the buffer region to keep the accuracy. Adequate buffer region can reduce the error of the subsystem partitioning. Another feature is to adopt the common Fermi level to all subsystems. By the common Fermi level, electrons and spins of subsystems can be non-integer number. Therefore, we can treat delocalized electron systems. So thanks to adopting the buffer region, the divide and conquer method can break any types of chemical bonds, from weak bond to single, double, triple, and conjugate bonds, as well as metallic bonds. Then we made an automatic fragmentation option in games. Therefore, the users need not care the fragmentations. This automatic fragmentation techniques makes possible to treat dynamically changing subsystems in the chemical reaction simulations. So this shows a sample input of the DC Hartree-Fock and DcMD2. So users only add the D and C and DC call name list and some parameters. Here, subtype equal auto correspond to the automatic fragmentations. So another feature of DC is a treatment of the delocalized electron systems. As I explained, the introduction of the common Fermi level makes possible to do that. Typical example is seen in the open shell system. The standard fragmentation, what is the fragment? What is the standard? But anyhow, the standard fragmentation method need to specify the spin density of each subsystems like this. But it is in the delocalized spin cases, so it is difficult or impossible to specify the spin states of each fragment. On the other hand, divide and conquer method need not to specify spin and spin state of each fragment. Actually, so that this is a sample input of the DC UHF. The user only input the charge and spin multiplicity of the whole system. Okay, and this shows some numerical result. We compare the DC UHF and standard UHF1. So you see the fragment, the spin charge density and the spin density extremely well, how can I say, agree well with each other. That this shows the errors. Okay, so let's move on to the main topic, DcDFTB program. So the motivation to develop our DcDFTBMD program was related with the K and the post-K computer project. So my mission in this project is to perform the chemical reaction dynamics simulations of nano and biosystems. So for reaction simulations, we need a quantum mechanics treatment. But if you compare between QMMD and classical MD, you can see there is a very big gap in size in between 1,000 and 10 million atoms. So to fill the gap was our motivation to develop the program. So we started to develop the DFTB calculation program in 2012. This shows the CPU time of the DFTB calculations by using our program. So 8,000 atoms calculation can be done only 2.5 hours. So of course, this is much faster than the standard ab initio calculation, but because the DFTB is a kind of a semi-empirical technique, okay? And construction of the DFTB Hamiltonian, that is similar to the Fock matrices in the Hartree-Fock constant DFT. And construction of DFT Hamiltonian was negligibly small. The diagonalization step is the main part of the DFTB calculations. Therefore, the computational cost increased cubic scaling. So then we combine the divide and conquer scheme with the DFTB calculation. So we found a tremendous acceleration was achieved like this one. So only 1 minute is needed for the DcDFTB calculation of 20,000 atoms. So such acceleration was achieved in the DC, was not achieved in the DC Hartree-Fock or DcDFTB calculations. So I think, so I can say the combination between the DFTB and the DC is ideal. So the DC scheme was suitable for massive parallel computation because we can assign each fragment to each node. Most of calculation can be done separately. So we developed the massive parallel DcDFTB code. And our program demonstrates high parallel. And then, so 1.5 million atoms calculation will be finished only 40 seconds by using the 128,000 CPU cores of K computer. So in the post-K computer project, we continued to modify the algorithm and program. For example, we make a FMM plus spline interpolation of for the PBC calculation. We accelerate for the PBC calculation. Also, we improve the memory access. So now 4.2 million atoms calculation can be done only 40 seconds for both without PBC and with PBC. We also try to extend the system size. The bottleneck was the memory size to save the charge-charge interaction function, so-called gamma AB and capital gamma AB in DFTB2 and DFTB3. So we developed the direct SCC, direct self-consistent charge algorithm to save the memory in the analogy of the direct SCF in the ab initio Hartree-Fock or DFT calculations. Then the maximum size of our program becomes more than 10 million atoms, like this one. So based on the success of the energy and gradient calculation by the DcDFTB method, we implemented the MD and metadynamics calculation code. As a DcDFTB energy calculation, DcDFTBMD and DcDFTB metad simulation performed MPI and OpenMP two-level parallelization. Recently, so we proposed hierarchical parallelization algorithm based on the multiple worker DcDFTB metad. So MPI worker, MPI subsystem, and OpenMP calculations. So the first application of DFTBMD simulation was a study on the proton diffusion in water. Because the proton diffusion involves the bond cleavage and formation, the classical MD simulation are not suitable to treat this one. Also, the proton diffusion is very ubiquitous. Therefore, it is QMMMD simulation is not suitable. So our result for both vehicular diffusion constant and Grotus diffusion constant were in good agreement with the experimental way, like this one. Also, from the temperature dependence, we estimate the proton transfer barrier for this one. So again, the obtained barrier was very reasonable. So we apply the DcDFTBMD simulation to nanotube and ice, proton diffusion in nanotube and ice. And then, so we found the high diffusivity in nanotube, like ice case. Because in nanotube, the water are structured even at the room temperatures. So we performed the reaction simulation for CO2 chemical absorption technique. So this is a target of the post-K computer project of ours. The reaction is controlled by temperature, 40 degrees Celsius in the absorption tower and 120 degrees Celsius in the regeneration towers. So the stoichiometric reaction formulas are given by forward and backboard reaction in those towers. But